We will next look at the related problem of one tank draining into another. Consider the situation shown in this diagram. There are two tanks, each with the same diameter, d sub t, and each open to the atmosphere with pressure P naught at the top of each tank. The tank on the left is filled with liquid to a height h1 that depends on time above the pipe connecting the two tanks. The tank on the right is filled to a height h2 above that pipe. The length of the pipe is capital L and its diameter is lowercase d. There's a net volumetric flow rate, capital Q, that depends on time from the tank with more liquid to the tank with less liquid under the influence of gravity. What we're asked to do is to determine the evolution in time of the height difference in the two liquid tanks, the difference between h1 of t and h2 of t, and study how the tanks approach steady state behavior, which would be they have the same liquid level in each. So the first thing we can do is we can apply the quasi-steady state approximation that we have just validated for our first example. So we'll first consider the steady state mechanical energy equation, which is listed again here in the handout on the website, on the course website for reference. So we have the difference in the kinetic energy terms plus pressure over density plus the potential energy terms from points 2 and point 1 multiplied by the mass flow rate is equal to the work done in the system minus the viscous losses in the straight conduits minus the viscous losses in fittings, valves, etc. So we'll return for a moment to our diagram. We'll write out our equation. So we have one half the average velocity u at position 2 cubed divided by the average velocity at position 2 plus P2 over the density rho plus G H2 multiplied by the mass flow rate W, which will be Q times rho. And that's going to be a constant in our system because whatever leaves tank 1 enters tank 2. And then we have minus the same thing written at position 1, which we'll define in a moment. So U1 cubed average divided by U1 average plus P1 over rho plus G H1 times W, and then this is now equal to the rate at which work is done in the system by moving surfaces minus 1/2 average U squared times the mass flow rate W times 4L over D times F, which will be the viscous losses due to friction factor in the pipe. And then we have to subtract out the sum over all fittings, etc. of the viscous losses due to these perturbations of the flow. So 1/2 average U squared times W times EV, the viscous loss coefficient. So we can check back. We see this is our mechanical energy balance simply reproduced. And as we've noted that for laminar flow, the average of the cube of the velocity is twice the cube of the average velocity. So if capital U is the mean velocity in the pipe, for laminar flow, the average of U cubed is 2 times capital U to the third. Whereas for turbulent flow, it's approximately just U cubed itself. So we can neglect that. Whereas for laminar flow, we have an extra factor of 2 in here. So in terms of viscous losses, we obviously have friction due to the wall friction in the pipe. And we also have a sudden contraction at the entrance to the pipe, and we have a sudden expansion at the end of the pipe. And so before we go any further, we want to define the two locations at which we're going to apply this equation. So we need position 1 and position 2. So an obvious thing to do is to take a position on the free surface in tank 1 and call this position 1, and we take another position on the free surface in tank 2 and call this position 2. Now this choice is motivated by several factors. One, the liquid heights will be changing slowly in our quasi-steady state or pseudo-steady approximation, so we can essentially neglect the velocity at points 1 and 2. But the second thing is the pressure is known. Because they're both in contact with the atmosphere at pressure P naught from the normal stress balance, the pressure in the liquid at position 1, position 2 at the free surfaces, that pressure is also equal to atmospheric pressure. So we know the pressure at both locations. We also know the heights at both locations relative to our reference plane, which is the top of the pipe. And then we can approximate the velocities as well. So, in general, once we figure out the viscous losses due to the contraction at the inlet and the expansion at the outlet, we'd also have to deal with the friction factor in the pipe. And so we'd have to use a correlation for turbulent flow based on the value of the Reynolds number. So we need some actual data to figure out if we can use the Blasius formula or this other formula with the logarithm listed here, depending on the range of Reynolds numbers we're considering. Then eventually, once the liquid levels are close enough in height, the flow will transition from turbulent to laminar. And so we'd have to switch and use a correlation for laminar flow at that point. But for simplicity, we'll consider the case where we're going to assume laminar flow. In the pipe connecting the two tanks. We're also going to neglect the effects of the contraction at the inlet and the expansion at the outlet of the pipe. So here's the inlet from tank 1 to the pipe where we have a sudden contraction, and we have a sudden expansion at the outlet of the pipe into tank 2. So neglect those effects as well, because that will allow us to get a more simplified version, a simplified expression for the velocity from this equation. So the main thing is the mechanical energy equation in the quasi-steady approximation provides an expression for the velocity as a function of other parameters in the system, such as the height difference, gravity, etc., work being done in the system if there is something like that. And once we have an expression for the velocity from the mechanical energy equation, we substitute into the unsteady form of the mass balance, and that allows us to obtain a differential equation for the change in the height of the liquid level in each of the tanks. If we neglect the effects of the contraction and expansion, we'll find for laminar flow that we get a much more simplified version or simplified expression for the velocity that allows us to make much more analytical progress. So, we've neglected the effects of the contraction and expansion at the inlet and outlet of the pipe. We've also have a case where there's no work being done in the system by moving surfaces. There's no pump, there's no rapid mixing or anything like that. So then the next thing we can do, we see there's a factor of W, the mass flow rate, that's common to each of these terms. So we can cancel off that expression, that factor of W. Moreover, we're going to assume that the liquid level in each tank very slowly in time. In other words, we're assuming that the volume of the liquid in each tank is very large relative to the volumetric or mass flow rate in the system. And as a result, we can essentially treat this as quasi-steady. Using the approximation we developed in the first example problem. And we can neglect the motion of liquid surfaces when we're applying the mechanical energy equation. Consequently, U1 and U2 can be treated as approximately 0 when we're dealing with the mechanical energy equation. So we can neglect this kinetic energy term here. We can neglect this kinetic energy term here. Moreover, pressure P2 is equal to P naught. That tank's open to the atmosphere. Same with pressure P1. It's open to the atmosphere, so that's pressure is P naught. Moreover, H2 is capital H2 of T, and H1 is capital H1 of T. So now, well, the last thing we can say is this U average is capital U squared. This entire term, where capital U is the mean velocity in the pipe. And Q is equal to pi over 4 d squared times capital U. Volumetric flow rate is just the cross-sectional area multiplied by the mean velocity in the pipe. So now, well, there's one last thing we can do. We also now, for laminar flow, need to determine the friction factor. So the friction factor for laminar flow is simply 16 over the Reynolds number. So we can write this out. (16 over Reynolds number), which is 16 times the kinematic viscosity divided by the mean velocity U times the pipe diameter. So now we can write the simplified form of the mechanical energy equation. What we find is that we have G times capital H2 from the first term minus G times capital H1 from the second term. So we have that G times the difference in heights of the liquid levels in the tanks, H2 of T minus H1 of T, is equal to this term, the friction factor term for flow in the pipe on the right hand side. So we get a minus 1/2 capital U squared, 4 times the pipe length L divided by the diameter, multiplied by F. And F is 16 nu divided by U times D. So we can see one of the U squareds cancels with this U here, and we have 16 times 4 over 2, which gives us 32. So we can now solve this expression here for the velocity U, which is the main goal of applying the mechanical energy equation. And we find that the mean velocity of the fluid in the pipe, capital U, which depends on time, is equal to G. There's a factor of D times D, so D squared, bringing that from the denominator on the right-hand side into the numerator on the left-hand side. Now we have the difference in heights. We'll take this minus sign and switch them around, so we'll get H1 of T minus H2 of T divided by 16 times 2 is 32 nu times L. So the steady form of the mechanical energy equation within our quasi-steady or pseudo-steady approximation has given us an expression for the velocity of the liquid in the pipe, subject to the constraints and assumptions of laminar flow, neglecting the viscous losses due to the expansion and contraction at the beginning and end of the pipe, and assuming that the liquid level changes slowly, so we can neglect the kinetic energy term at the surface of each of the liquid levels in the tanks. So that's the first part. That's the result of our steady state mechanical energy equation. Now we want to apply unsteady mass balance. So if we look at the unsteady mass balance, we have the time derivative of the total mass of fluid in the tank, integral of rho dV, is equal to minus the surface integral over various surfaces where there's inlet and outlet. So let's say the top surface, which is a free surface, we have n dotted with u minus vs ds with a factor of rho, and then minus the integral over the surface of the pipe of rho n dotted with u minus vs ds. And so the top surface of the control volume for applying the unsteady mass balance, if we apply our mass balance here, to this dashed region, in fact, let's just consider essentially liquid up to the height of the pipe, which would be h1 of t. So we can essentially consider this liquid here. Anything below this would never leave the tank. So this is our V of t. Then we're applying our unsteady mass balance. We see on the top surface of the liquid that because the top of the control volume moves downward with the velocity of the liquid, u minus vs is equal to 0, just as it was in our previous problem. And as a result, this first surface integral vanishes. On the pipe, the control volume surface is not moving, so vs is equal to 0, and n dot u is simply u in the pipe. So the first term here becomes the time derivative. The density is constant. The integral of the density over the volume is rho times v of t, and that's equal to minus rho u, which is the mean velocity of the pipe, multiplied by the pipe cross-sectional area, pi over 4 d squared. Or if we cancel out the density, what we're saying is the rate of change of the volume in our control volume is equal to minus q, minus the volumetric flow rate that exits from the pipe. Now the volume, and this was all for tank 1, the volume becomes simply pi over 4 tank diameter squared times h1 of t, and that's equal to minus pi over 4 d squared u, which is minus q of t. And u we can substitute eventually from our steady state mechanical energy equation. So the final result for this, if we do a little bit of simplification, this pi over 4 cancels that pi over 4, and we find that dh1 dt is equal to minus d, the pipe diameter, divided by dt, the tank diameter, squared times capital U, the mean flow rate or mean velocity through the pipe. And there's actually a minus sign out in front that we have over here. So we'll highlight this expression. And now we can do the same thing for tank 2. We can apply the unsteady mass balance. So for tank 2, what we get is d by dt of v2 of t is equal to plus q, because now the liquid is flowing out of tank 1, it's flowing into tank 2. And q, once again, is equal to pi over 4 pipe diameter squared times u, the mean velocity in the pipe. And if we substitute for v2, which is just pi over 4 dt squared h2 of t, we obtain the differential equation for the change in h2 with respect to time that looks very much like the one we had for tank 1. The only difference is there's no minus sign in this case, it's just d over dt squared times capital U. So now we have two expressions that tell us how the height of the liquid level in each tank changes as a function of the flow rate, or the velocity u, into or out of the tank through the pipe. We have an expression for u from our steady state mechanical energy equation that involves a difference between h1 and h2. So this suggests is that we could subtract the results of our two unsteady mass balances. We have an h1 minus h2 in our expression for u of t, and so it will be useful to get h1 minus h2 in our mass balance differential equation. So if we do that now, we simply subtract the second mass balance from the first, and therefore we get d h1 of t minus h2 of t dt is equal to minus d over dt squared u minus d over dt squared u. So we get a minus 2 d over dt quantity squared times capital U, which, if we use our expression for u that we have from the mechanical energy equation just above here, we can rewrite this in terms of the difference between h1 and h2. So 2 divided by 32 gives us 1 over 16, and so we get a minus g d to the fourth h1 of t minus h2 of t divided by 16 nu dt, the tank diameter, squared times L, the length of the pipe. So this is now a differential equation that tells how the difference between the liquid levels in the two tanks evolves in time. It's a first order ordinary differential equation. We need one initial condition. So our initial condition at time 0, h1 of 0 minus h2 of 0 would be equal to something we'll call h naught, the initial difference between the liquid levels in the two tanks. So now we can simply separate variables, with our variable being h1 minus h2, and integrate. So we get d h1 minus h2. On the left-hand side, we divide by h1 minus h2, so we get h1 minus h2. And that will now be equal to minus g d to the fourth divided by 16 nu dt squared times L dt. We can now integrate each side of this equation. Everything here out in front of dt is a constant, so we can simply put the integral sign here. And we find left-hand side, it's dx over x, essentially. So we get the logarithm of h1 minus h2 is equal to minus g d to the fourth t divided by 16 nu dt squared L plus a constant of integration that we'll call C1. We can now apply the initial condition. At time t equals 0, h1 minus h2 is h naught. So we have the log of h naught is equal to 0 plus C1. And so obviously C1 is equal to the log of h naught, which is the same as the log of h1 of 0 minus h2 of 0. So now we can just substitute for C1 back into this equation and then bring it to the left-hand side. So we get the log of h1 of t minus h2 of t minus C1, which is minus the log of h1 of 0 minus h2 of 0 is equal to the rest of these terms here, which is the minus g d to the fourth t divided by 16 nu dt squared L. Now, the difference between two logs is simply the log of the ratio of those two terms. The left-hand side is the logarithm of h1 minus h2 over h1 of 0 minus h2 of 0. And so then we can take the exponential of each side of this equation and get our final result. And so what we find is that after we exponentiate it, we have h1 of t minus h2 of t divided by the initial height difference, h1 of 0 minus h2 of 0 is equal to the exponential of minus g d to the fourth t divided by 16 nu dt squared times L. And so we can see that the difference in the levels of the tanks approaches 0 as an exponential decay. And so as the liquid levels get closer and closer, the rate at which they change becomes smaller and smaller. And it becomes smaller exponentially within the approximations we made. Now this makes perfect sense because the driving force for this flow from one tank to the other is the hydrostatic pressure component. It's the potential energy difference. It's the height of liquid in level 1 being higher than the height of the liquid level in tank 2. So as time progresses and the height in liquid 1 and height in tank 1 decreases, the height in tank 2 increases, the driving force, the difference in those two heights, the potential energy term G H1 minus H2, will become smaller and smaller. And that results in the exponential decay in the rate at which the height difference decreases in time. Now we've obviously made some approximations. We've neglected the viscous losses at the inlet and outlet of the pipe, the contraction and the expansion. That would alter this result somewhat. You wouldn't have as nice of a formula like this. You might actually have to integrate the resulting equation numerically. But this is a very good approximation within the constraints we're given for the problem. Now in general, the flow will initially be, especially for tanks of industrial scale, the flow will initially be turbulent. So one would have to take a friction factor expression for turbulent flow into the mechanical energy equation. So either the velocious equation, 0.0791 Reynolds to minus 1/4, or this logarithmic expression is valid for even higher values of the Reynolds number. you'd compute with that until the liquid level drops to the difference in heights at which the flow transitions from turbulent to laminar. And we can do that if we have numerical values by figuring out when the Reynolds number, what the velocity would be in the pipe, or what the volumetric flow rate would be in the pipe when the Reynolds number transitions to about 2100. And we could figure out what the height difference would be at that point in time. So we would have to integrate this equation numerically using the expressions for turbulent flow until we get to that height difference. Then we'd have to stop and switch to using the friction factor F for laminar flow that we used in this problem and continue the integration from then until whatever stopping time we want. Now, in fact, it assumes it will take an infinite amount of time to actually get the liquid levels to be equal, but for all practical purposes, the difference will be negligible once time reaches a certain value. So you can say once this difference in heights is equal to, let's say, 1/10 or 1/100th of its initial value, then we can consider that to be the stopping time when the things will be equal. In fact, if you include the other frictional or other viscous losses at the expansion and contraction at the beginning and inlet and outlet of the pipe, you would find different terms and you wouldn't get this exponential decay. You would get a different functional form, and in that case, it might actually reach zero, this height difference, in a finite amount of time. So this problem is a good example of the quasi-steady approximation. Again, it's including or combining the steady state version of the mechanical energy equation, or Bernoulli's equation, which it essentially simplifies to if all viscous losses are neglected. You combine that steady mechanical energy equation with the unsteady mass balance equation, and as we've seen previously, this is very accurate for any kind of tank graining problem, and so we're able to successfully apply it in this situation to get this result.